Science. Presents. Vectors, in Physics. Part 1. Introduction to Cartesian and Polar Coordinate Systems. As you see, the title of this video suggests that it's about the vectors in physics. Actually, this is a short course on vectors, especially for the higher secondary school physics. At secondary or higher secondary school level, our students struggle with vectors, in order to bring them in their daily practices. The question is, why we need to understand and practice vectors. Because in physics we mostly deal with forces of nature, and the forces of nature are represented with vectors. In this video tutorials series, or I should say, in this video lectures course, we'll start from the very beginning, and we'll try to go farther, as much as we could go, until we understand vectors and use them, in our daily physics lessons. Let's begin with a very simple question. What is a vector by definition in physics? A vector is a quantity that has both magnitude and direction. It is typically represented by an arrow whose direction is the same as that of the quantity, and whose length is proportional to the quantity's magnitude. Before we go further, we need to revise the basics of coordinate system, especially the Cartesian coordinates. Let me show you how to draw a Cartesian coordinates system. Here, horizontal pink line represents the x-axis and the vertical green line represents the y-axis. There is something called units. Units are equal. They add up and increase as soon as something travels along x or y-axis. As we can see, that x-axis is at an angle of 90 degrees relative to y-axis, and same is true for y-axis, means y-axis is also at 90 degrees, relative to x-axis. For those students who practice vectors on some electronic device, there is a great software application on internet, called GeoGebra. This is GeoGebra. The only biggest application for algebra, geometry, calculus and so many other practices of mathematics. Let me change its background color to black, because I want to match its color scheme with our class environment. GeoGebra is precise, accurate, and very dynamic. In Cartesian coordinate system of GeoGebra, we can see now, there are 4 quadrants of this two-dimensional plane. Two-dimensional Cartesian coordinates system is sometimes drawn inside a circle. On a circle, the x-axis becomes 0 to 180 degrees, and the y-axis becomes 90 to 270 degrees of angles. If we want to be more specific, we can say, x becomes 0 or 360 degrees, minus x becomes 180 degrees, y becomes 90 degrees and minus y becomes 270 degrees of angles. In GeoGebra, you can draw by putting mathematical values as well. For example, if we have a two-dimensional Cartesian coordinates system inside a circle, we can understand, how do Cartesian coordinates work? Using angular values. Keep in mind that another term for angular values is polar coordinates. When you put a polar coordinate value for a vector, you have to tell GeoGebra the magnitude of the vector in form of length, and its direction as the angular value. Suppose you want to draw a force vector in GeoGebra, with polar coordinates. You need to put given values in this text field. But first you need to specify the point where your vector ends. For example, our vector is a 4 Newton magnitude and its direction is straight towards east. Conventionally, east is always at an angle of 0 degrees, relative to conventional x-axis. And north is always at 90 degrees, relative to x-axis. So, when someone says that the direction is straight towards east, it means the direction is at the angle of 0 degrees relative to x-axis. Therefore, a vector of 4 Newton towards east should look like this. In GeoGebra, we type values in such a manner that the software could read and execute them. For a vector of 4 Newton force towards east, first, we'll type in the point where our vector ends, which is 4 units at the angle of 0 degrees. Now look at the point in GeoGebra's workspace. This blue dot here. This is the point where our vector should end, if it is a 4-unit long vector. But why this blue dot is exactly on the horizontal x-axis is line? It is because we gave it the angular value of 0 degrees. Now, we are ready to draw our vector. All we need is to tell GeoGebra that we want a vector from origin to our newly created point P. Here you can see, GeoGebra is asking for the start and end points. We know that our start point is the origin 0 of coordinate system, and the end point of our vector is the point P. If you look closely at origin, GeoGebra has assigned a name automatically to the start point. It is capital A. Let's tell GeoGebra that our vector starts from point A, and it ends on point P. GeoGebra loves points, especially the coordinate points. Type A for the start point, and P for the end point, in this text field. You can see, we've created our vector, which is exactly 4 units on x-axis, and its direction is the angle of 0 degrees on x-axis. So, what we found here, is that, in Cartesian coordinate system, angles are also important, because, whenever we need to tell the direction of some force vector, we need to tell it in polar or angular values. But if we are not given the direction in some angle of theta, we can still find the direction of a vector, just by using the absolute coordinate values. Absolute values are simple. Simply, there are two numbers, with either plus or minus signs, like for example, +5, -6. As we saw earlier in this video, that there are 4 quadrants in a Cartesian coordinate system. Conventionally we count them in a counterclockwise manner. In first quadrant, values for both x and y coordinates are positive, so this is plus quadrant. In second quadrant, the value for x is now negative. But for y, it is still positive. Therefore, this quadrant is minus plus quadrant. Third quadrant is minus quadrant, because values for both x and y are negative now. Fourth, and last quadrant is of course, plus quadrant, because the value for x is positive, and the value for y is still negative. It means, when we are given a value, in form of two numbers, one for x-axis, and the other for y-axis, we actually are able to draw a point, on a Cartesian coordinate system. And that point is a specific location in space. If we have two values for two different points, it means we know the magnitude and direction of a vector, without having the polar coordinates in degrees. In a nutshell, a coordinate system is all we need for practicing and producing vectors. That is why we should pay some extra deep and special attention towards the concept of coordinate system. Coordinate systems, vectors, grids and graphs, are now widely used in other disciplines for various purposes. But for us students of physics, coordinate system is like a ground to step on, draw, work, walk, jump, run and play on. Actually, for a student of physics, it's everything. Usually we use two-dimensional coordinate systems. However, a three-dimensional coordinate system is the actual Cartesian coordinate system. We know that in a two-dimensional coordinate system, there are 4 quadrants. But in a three-dimensional coordinate system, there are 8 quadrants. When we draw all possible angles from the origin in a 2D coordinate system, they complete a circle. But when we draw all possible angles, from the origin, in a 3D coordinate system, angles complete a sphere. So, now we know what are coordinates. But without practice, we can't use them properly. We need a lot of practice, of using absolute and polar values, in order to draw vectors. Although, drawing points and vectors, pen to paper, is always an ideal thing to do, but if someone is using electronic devices, GeoGebra is the place, as I suggested earlier in this video. GeoGebra also has a three-dimensional workspace. We have to tell GeoGebra all three of the coordinate values, in order to draw a point, in three-dimensional space, as the start or end point of some vector. Suppose we have a vector, starting from points, 3 on x, 2 on y, and 9 on z, and ending at points, 0 on x, 0 on y and 2 on z. So now, we have all three axes at the same time, and not only the x and y axes. This time we have a value for z-axis, as well. It means we require 3D workspace. Using GeoGebra's 3D workspace, we can draw our vector, just by simply putting the values in this text field. As soon as we put values in here, GeoGebra's workspace updates automatically. As you can see, our first point has been created, as soon as we've told the coordinates to GeoGebra. Now, what is the second, or endpoint of our vector? We have a value of 0 on positive x, 0 on positive y also, and 2 on positive z. Let's put these values in the input field of GeoGebra. This is the second, or endpoint, of our vector. Now, we are ready to create a vector. Simply type in the word vector, and tell the software that your vector starts from point 1, and it ends on point 2.